Okay, I'm recording. Yeah. So we're in the third one, sec-butyl. It's 3 carbons, basically a propyl group. That is a propyl group, 3 carbons, with a methyl on carbon number 1. And the systematic name would be 1-methyl-propyl. And then tert-butyl, which all the butyls are 4 carbons total, right? Of course, you can see the 4 carbons. It's 4 carbons, right? And so tert-butyl, the alternate systematic name is, you envision the 2 carbon piece, ethyl, with a methyl on number 1 and another methyl on number 1. So the name is 1,1-dimethyl ethyl. All right, so we did that last time. I'm gonna just try two of these practice problems real quick. Oops. I'm gonna do one of these ones, which are draw the molecule and provide an alternate name. Okay, so I'm going to switch to my webcam. You might want to write this down, like 1,1,1-trifluoro 4,1,1-dimethyl ethyl octane. Write that down on your paper, top one, all right? 1,1,1-trifluoro 4,1,1-dimethyl ethyl octane. And I'm going to switch to my other webcam, and I'll write it down again also. Okay. All right, let's see if I can do that. 1,1,1-trifluoro 1,1,1-trifluoro 4, 1,1 dimethyl ethyl octane. All right, so I'm going to try to draw this out as a zigzag first. That would help. Draw it out as a zigzag, and then when I say zigzag, I mean skeletal, right? And then we'll add everything in, and then we'll try to convert it to the alternate name. So octane, start with octane. You always go from the right to left. I see octane, so I'm like 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Whoops, too many. So now I got 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Got it. And now 1,1,1-trifluoro. So how do I draw that? 1,1,1-trifluoro. Well, that looks like I have 3 fluorines on carbon 1. So 1, 2, 3 of them. F, F, F. I have my 3 fluorines on carbon 1. Maybe useful to draw in your numbers too. 1, 2, 3, 4, 5, 6, 7, 8. There's your numbers. That really helps to avoid little mistakes, right? Draw in your numbers. Okay. All right, and then it looks like on carbon 4, we have a 1,1-dimethyl ethyl group. A 1,1-dimethyl ethyl. Do you guys, from the little chart, do you know which one that is? It's one of the butyls. You get, remember, your class is open notes. having that sheet printed out would be probably useful.
Tert-butyl.
Yep, tert-butyl. And so it's a tert-butyl one, and this is from memory, and it takes a little while to memorize these, but it's like a carbon with methyl, 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 right? It's a little like a central carbon with 3 methyls on it, and of course that makes sense for 1,1-dimethyl ethyl, because it's like you have a 2 carbon piece, pick 2 carbons, 1 and 2, and it's a dimethyl. So it's carbon 1 of those 2 has 2 methyls. So how do you memorize that's tert-butyl? I really think the best way is just to plain old memorize it. It's plain old memorization. Okay, so I'm going to do one more. Oh yeah, no, and sorry, we need to come up with the alternate name. So the alternate name will also be something octane, right? Okay, something octane, right? And the 1,1,1-trifluoro will still be part of that name. I'm getting a little bit weird of a darkening effect. I don't know if you can see it, but okay. I don't know why it's doing that. I don't know. Yeah, okay. All right, so we have octane, right? So the alternate name is not going to use 1,1-dimethyl ethyl. The alternate is going to use tert-butyl, right? So what I would do is on the left, just like write our substituents kind of listed, not like horizontally, almost vertically. So it's 1,1,1 trifluoro. Because we may have to alphabetize these, and if we have them listed, it's kind of easy to resort them and re-alphabetize them. And then what's on carbon 4? It's a something butyl, right? It's a tert-butyl. Tert-butyl, got it? Okay, so now the question is, of these two lines, trifluoro and tert-butyl, what do we alphabetize on? So this is going back to last lecture a bit. On the top one, is it by the T or the F? Anybody know?
By the T?
It's actually the F. That was the weird thing. It's the F, yeah. And I maybe underline it. It's like, yeah, if you just have some like fluorines or bromines or chlorines or like dichloro, trichloro, tetrachloro, tribromo, it's always going to be the letter of the substituent, like the F. And tert-butyl, from last slide, we remember, is it the T or the B?
The B.
It's the B, yeah. So these are backwards. I just got to put the tert-butyl on top and we're done. Okay?
Professor,
Yeah.
some of us are, I'm realizing some students can't see their piece of paper, apparently.
Okay. Let me see.
You have to stop sharing your screen on your main.
Oh, I'm sorry. Yeah, okay. Thank you for, there we go. Okay, so let's pretend that I didn't write the bottom stuff. Okay, so let's step forward. Yeah, thanks for catching that. And if it looks like I screw that up again in the future, just remind me. Okay, so the first thing I did was I looked at the name. Oh, yeah? And then I started with octane, and I'm like, well, that would be a good way to, you know, the 8 carbons would be a good place to start. So I drew out octane, 1, 2, 3, 4, 5, 6, 7, 8, right? The next thing I did is I filled in the 1,1,1 trifluoro and the 4,1,1-dimethyl ethyl. Okay, great. I also added numbers. I strongly recommend that you fill in the numbers. That you'll avoid a lot of mistakes if you just add those numbers to my octane. It's 8 carbons, right? All right, and then I added the trifluoro to carbon 1. And then I added on carbon 4 the dimethyl ethyl, also called a tert-butyl group, right? And then the next thing I did was I wanted to convert it to a systematic naming. This is called common naming. This is I'm sorry, no, this is systematic up here. Common is tert-butyl, okay? So I want to practice going from the systematic name to the common name, all right? That's what I did below. First thing I did was just write octane, right? That's a good start. Always start with the right hand of the name. And then what I did was I added the thing that didn't change is 1,1,1 trifluoro, right? That's not changing. So now we have 1,1,1 trifluoro, octane. And the other thing is that I usually stack these vertically. So I like add that guy vertically underneath. Now it's called 4-tert-butyl, okay? The next thing I did was I underlined where I alphabetized by. From last lecture, you would remember that if it's something like trifluoro, tribromo, dichloro, dibromo, you never go by the T, you go by the F, okay? That was from last lecture. Okay, and then the other one is a tert-butyl, and now we could either alphabetize by the T or the B. We have the silly rule sheet, last sheet, and it said by the B. So this is the name. It's just what I screwed up is the tert-butyl has got to be on top, right? So, so all I'm going to do is erase the bottom tert-butyl and just write it up, sneak it up top. So it's going to be 4-tert-butyl. Okay, and just erase or whatever. So this is the full name. I'm happy if you guys leave these written like this, or you can write it all out. I mean, if I was writing the full answer, it would be 4-tert butyl dash 1, 1, 1 trifluoro octane, right? I'm cool with either this kind of written out thing, or if you just write the things horizontally, I'm cool with that too. Okay, there's our, sorry, it's a little messy. It's terbutyl, 4-terbutyl, okay? All right, now from the PowerPoint, I'm gonna do one from the bottom, which you guys can't see. It's in the notes. I'll just pick one. It's 5-isobutyl nonane. So we'll do one more. This is from the bottom half of the slide, which you cannot see. So I'm just gonna write it though. 5-isobutyl nonane. 5-isobutyl nonane. And now we're going to draw it and then convert it from the common name to the systematic name. What's nonane? How many carbons?
9
9.
carbons.
9. So just start with 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe I like to get my second color out, and I'm like, that's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, and I screwed up. So get your eraser out. Remember, you should always have a nice eraser, because this is a course where you always make little mistakes. If you have an unerasable pen, you're gonna hate yourself. So, all right, and then on carbon 5, we have an isobutyl. So here you'd have to go look it up on that chart. It's how many carbons though? Isobutyl. Butyl is 4, right? So you, from memory or from your that little cheat sheet, you'd say, well, isobutyl is a 4-carbon piece that looks on carbon 5 like that. That's an isobutyl group, and that there's no way to really learn that except memorization. That is pure memorization. Okay. With
And
practice, you're just going to get them. But
there's 2 hydrogens bonded to that first carbon on the isobutyl, correct?
there's 1 hydrogen right there. Yeah.
And then 2 on the one below that
Yep.
one.
2. So it goes 1, 2, 1, and these are 3 and 3. All right. So let's do the systematic naming. Now you could either memorize the systematic name, or we can kind of recalculate it, or redetermine it. Because off the main chain, off carbon 5, it's like we have a 1. I'm going to circle these 1, 2, and 3, right? It's like we start renumbering, right? 1, 2, 3. Okay. 1, 2, 3. So what's a 3-carbon piece? Like if we just had a 3-carbon piece, it'd be a what substituent?
Propyl.
Propyl, yeah. But on this propyl, we have a methyl on number 2. So it's 2-methylpropyl. And the way we just put this together now, this is really easy because there's nothing else on the molecule. It's just 5, blah, 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 nonane, right? Now the blah, blah, blah is in parentheses. And it's 5, it's going to be 2-methylpropyl. 5, 2-methylpropyl. Five 2-methylpropyl. That's all there is to it. I know it's a little weird at first. With a little bit of practice, you know, I'll do all the practice problems I suggested and look in the book for some more, and you will be an expert at this. Right? We got to move on. Going back to PowerPoint. All right, and hello. All right, here I am. There you guys are. All right. So yeah, try these other problems. That'll help to get kind of master this. And just think about the alphabetization rules. And if you would do an exam or a quiz problem with a silly little alphabetization rule problem, that's not like lose everything. That's a minor thing. So those are the kind of nitpick points we would take off. Is you get everything, but your alphabetization's wrong. Yeah, that's not the end of the world, right? Okay. All right, so this is a little nomenclature issue. It's useful to distinguish the different types of carbons and hydrogens in a molecule. A primary carbon, so this is, we can either talk about carbons and hydrogens, and a primary carbon has one carbon attached to it. And you can see this example of this molecule. This CH3 up here is a primary carbon, and the primary carbon, a primary carbon will have one carbon attached to it, right? Whereas a secondary carbon has two carbons attached to it. So it's just a classification system, right? So a secondary carbon has two carbons attached to it. So this is a secondary carbon. And then we have a tertiary carbon, which has three things on it. So we have one tertiary carbon here. It's the central carbon. It's called a tertiary carbon. So all we're doing is classifying the different carbons, the primary carbon, secondary carbon, and tertiary carbon. We're going to see that again. So not that useful right now. We're going to use it a ton in the next chapter. So we'll talk about, oh, this is a primary carbon. Oh, this is a secondary carbon. That's what we're talking about. And we can also, this does not have any quaternary. What would a quaternary carbon have? 4 carbons on it, okay? So we have primary, secondary, tertiary, and quaternary carbons. We also have hydrogens. So like on a primary, like this hydrogen's a primary hydrogen. And on the, so the hydrogens on a primary carbon, the hydrogens on a primary carbon are also called primary. So these are primary hydrogens, and this is a primary carbon. So we're going to be able to talk about, we're going to be able to identify the different kinds of carbons and the different kinds of hydrogens and give them a classification system. What kind of hydrogens are these? They're secondary, and the secondary hydrogens are on a secondary carbon, okay? And then we have a tertiary hydrogen. What kind of carbon is a tertiary hydrogen attached to? A tertiary carbon, right? So anyway, keep those names in the back of your mind. We'll see them probably, maybe even at the end of this lecture once we're in chapter 3, okay? Just remember this primary, secondary, tertiary business, all right? Alkanes, so all the like methane, ethane, butane, propane, pentane, hexane, they all have kind of a regular structure. They're really boring, we'll say. They're very tetrahedral, 109.5 roughly. CC bond lengths around 1.5 angstroms. You don't need to know that. So they're very tetrahedral, just kind of very regular. It's a regular structure, okay? They typically adopt a zigzag structure. So as you start getting larger and larger, they just kind of zigzag longer and longer away, because that minimizes the energy of them all, okay? So this is an example. It looks like hexane, right? 1, 2, 3, 4, 5, 6. It's hexane. So hexane would adopt this kind of zigzaggy structure. And that just keeps everything as far apart as possible. It's very happy in that kind of zigzag structure. This is the space filling model of the same thing. It just shows everything as a sort of spherical ball type thing. Okay, and as you get longer and longer, so the x-axis is the number of carbons, the density starts increasing, the boiling point starts increasing, and the melting point starts increasing. So there's more and more interactions between the molecules. So when the two molecules start stacking on top of each other, you probably have heard about that in Gen Chem. London dispersion. It's like one of these intermolecular forces. Molecules start connecting a little bit non-covalently. And as you add more carbons, they have this effect. And it's a surface area dependent effect. So you start adding more and more carbons, there's more of a surface area effect. And things like boiling point and melting point increase. The density increases because they can all stack on top of each other really efficiently. Okay. These attractive forces are due to induced dipole forces. What does that mean? Well, we know what a dipole is, right? What's a dipole? It's like delta positive, delta negative, right? I have two things, maybe they're bouncing into each other. And when they bounce into each other, you make these temporary dipoles, delta minus, delta plus, and that is a slight attractive force. This kind of shows it for pentane. So pentane, the molecules are slapping into each other, these linear molecules. When they do that, they create little mini dipoles, and that they're attractive, right? What do you think happens if you start adding more carbons? There's more interactions, right? You add more interactions, and what happens to your boiling point, your melting point? They increase. That's exactly what happens. So the London forces, what's that?
Can you elaborate a little bit on when you say they smack into each other, how that creates a dipole effect?
It's just a property of the when things collide. When it collides, it affects the electronics a little bit, and something might become a little positive, something might become a little negative, and that's just a very slight interactive force. It's non-covalent, right? It's not like hydrogen bonding. Well, hydrogen bonding is non-covalent too, but it's not as intense as hydrogen bonding. So you just get these little partial positive charges, partial negative charges. And when is this the most profound? Is if you have a long stringy molecule, right? Lots of atoms in a row, lots of atoms in a row, you get more of these, right? And when is it less profound? When the molecules are branched, like you have all sorts of branching, the molecules then are more of a ball. And a ball type structure has less of this interaction. The best interaction is if you have long stringy things that can kind of attach, like interact as a string, right? Two strings have a lot of surface area. So long stringy molecules have more of an effect. And who has less of an effect? What's the word? Branched. If you have like a bunch of CH3s on a tert-butyl group or something, branched. And those kind of things have less of an effect, and you're gonna have less of boiling point increases and all sorts of stuff like that. So branched alkanes have smaller surface areas than their linear isomers. So the melting point and boiling point are lower. That's a general rule. Who has the highest boiling point? Like if I have 5 carbons in a row, or 5 carbons that are kind of branched out, the 5 carbons in the row are going to have the highest boiling point. All right. Yeah. Okay. Last couple topics in chapter 2. Rotation of single bonds. And so we're going to talk about the structure of ethane, propane, and butane. All right. All right. So ethane. How is ethane a complicated molecule? It's not a complicated molecule. It's 2 carbons, right? So these are going to go from some very non-complicated to a little more complicated to a tad more complicated. But these are not that crazy. Ethane, how many carbons are in ethane? 2. Right. So let's think about ethane. And if you think about the structure of ethane, it's 2 CH3s. And there's basically 2 conformational states. One where everything's kind of far apart from each other, right? And one where you rotate the bond a little bit. And now everything's kind of aligned, right? Everything's aligned. See how we see how the top, all the hydrogens are aligned now with the neighbors, yeah? And then it rotates back, okay? Who's the happy? The middle or the sides? So who's the happiest here? The left and right, which are basically the same idea, or who's the least happy of these?
The middle is the least happy.
Yeah. The middle is the least happy because there's a little bit of an interaction between the neighboring H's. They're not bumping into each other, but what it is the electron clouds. You have electron cloud, electron cloud, electron cloud. There's all these electron clouds, and there's a little bit of an interaction, right? And that makes the middle a little less happy, okay? All right. And the left and right are a little happier, okay? Okay, and this kind of shows the same thing. We just have all sorts of weird colors for the H's. All right? I'm gonna give some names for, I'm gonna give names for the left and right. I'm gonna call those staggered. You might wanna write that down. Staggered are the happy ones. Staggered and staggered, okay? Staggered. I always misspell it, so you might have to Google the spelling, staggered. It's either 2 G's or 2 R's, I always forget. And then the middle one has another name, it's called eclipsed, okay? Eclipsed, E-C-L-I-P-S-E-D. Eclipsed is a little less happy, right? Okay. Staggered, oh, there they are. And I think I might have still misspelled it, but there it is, staggered, eclipsed, staggered. All right, eclipsed is a little less happy, okay? All right, there's this concept called Newman projections. It depicts the conformations of rotatable bonds. It's just a different way of drawing the molecules, okay? So this is a little weird. It's not that crazy. Just give me a second on it. So imagine we're looking at ethane from the left. That's our face. We're looking at the molecule, right? We're looking off in the plane of the computer screen at the carbon. What is directly high? It's the hydrogen, right? And then you have a H that's going down to the left and an H that's going down to the right, because this is our perspective, right? Right? We have a close carbon and we have a further carbon, right? If we're over here, we have a close carbon and we have a further carbon, right? And all the Newman projection is doing is allowing us to depict what we see in this is the Newman projection over here, right? Okay, so what it looks like is a weird, like little, like three bonds diverging from the central point, and that is what we're calling the front carbon. The front carbon, which is this carbon, right? That's the front carbon based on our perspective, if we're in the board or the computer. And what's the circle? There's a circle that depicts the back carbon. The back carbon, which in this case is this carbon, right? That make sense? Based on us being over here, this is the close carbon and this is the far carbon. The close carbon is the little dot with the 3 things on it. The back carbon is a circle. And all we're doing is showing where the hydrogens are, right? This is another kind of way to sort of show it. Yeah, I'll try to do this in molecular models. Also, I have my models. This is much easier in class because our perspective is the same. You might want to use your own models for this exercise a little bit, but this is a little hard because I'm looking at you and you're looking at me and we have different perspectives, right? So I'm probably going to have to skip my models for this, but if you have your models, you can try to follow along, right? This down here, though, shows us kind of, the perspective of the Newman projection. This is the close carbon, that's the far carbon, right? This is what we're seeing up here, right? This is what we're seeing, and this is another way to show it, and your models are a great way to see this too, right? All right. And what's this one called? Is this the staggered or eclipsed? Somebody say.
Eclipse?
No, this is staggered actually. The staggered is everything kind of away from each other. The eclipsed is everything lined up. So if we rotate this 60 degrees, it would be eclipsed, but this is staggered actually. Okay, so we get the basic idea of a Newman projection. All it is you have a kind of a dot, which is the close carbon, circle is the far carbon, and then you just draw what you see. Okay, so rotamers, which just means the rotational isomers, have different potential energies. So you have happy and unhappy. We already said that, right? The most stable is staggered. The least stable is eclipsed. It's actually a transition state between the staggered. Now this just shows it in an energetic depiction. So we see the staggered down here. And there's a little bit of an energy barrier as you go from this staggered to the eclipsed, down to the next staggered, up to the eclipsed, down to the next staggered, up to the eclipse. They're all the same, right? You're just rotating two bonds, right? I'm taking ethane and I'm just kind of rotating. And with my models, it's staggered, eclipse, right? There's a staggered, eclipsed, staggered, eclipsed, staggered, eclipsed. You probably have to do this with your own models as well. And office hours too, you know, if you get stuck, I can step through this a little bit more. This is not that bad, though, I hope. Okay, we have staggered, we have eclipsed. And what's the energy barrier? It's 2.9 kilocalories per mole. It's a very minor energy barrier. At room temperature, this is happening like crazy. If you have ethane, it's just alternating back and forth, back and forth, back and forth, right? Okay, we cool with ethane. Ethane's not that bad. Let me give you one more name for eclipsed and the unhappy eclipsed. We're going to call it torsional strain. So torsional strain, and I wish I could write it up here, or you could write it. Torsional strain occurs with eclipsed molecules. And all that means is the electron clouds are bumping into each other. Electron clouds are bumping into each other, right? That's why these eclipsed on the top are not as happy, okay? Now propane. Okay, so all we did is we added an extra carbon, propane now. The rotamers of propane are very similar to ethane. The rotamers of propane are similar, okay? If you look at it, the bottom is also staggered, and it goes eclipsed, staggered, eclipsed, staggered, eclipsed, staggered. It's the same idea. What's different though? The energy barrier is slightly higher. It's just a little more energy because there's, you know, you have an extra atom and it has a little more of an interactive force. So nothing different. Ethane and propane, basically the same, all right? You still got staggered, you still got eclipsed, all right? Now comes the slightly crazier one, butane. We cool with propane? Just a little bit more energy, just a little more. Butane is just a little different because there's now going to be 4 different rotamer types. There's 4 different ones, but they're all, it's not that crazy. Okay, so there are 2 low energy staggered. There's 2 low energy staggered arrangements where the methyl groups, one is where the methyl groups are 180 degrees apart, and it's anti. And I will try to show this with my models, and we'll see the Newman in a second. You can kind of, I don't know if you can see it too well. See how I have 2 methyls at the end? It's 4 carbons, right? Carbon, this is a little hard on my tiny computer, on my tiny screen, but we have 4 carbons, and we're looking down the central bond, right? The central bond is what we're looking down. And the CH3, one's up and one's down. That's what we're calling, it's the very happy. This is the happy, happy, happy one, right? Of course, everything's far apart. It's going to be happy, right? And then there's going to be another one where the methyls are 60 degrees apart. I'm just going to show this. This staggered one is going to be it's up here. You can kind of, it's hard for you to see. I'm having difficulty showing this on my webcam, but the Newmans will help. Okay, so this is the alternate staggered. It's staggered though. Okay, the Newmans are really going to help, but that's staggered. This has a French name. It's called gauche, G-A-U-C-H, which I don't know anything about the French language except that gauche I think means kind of awkward, and this is a little bit awkward. And it's, you think this is happy compared to the other one? It's a little less happy than the one where everything's far apart, okay? So the top one, we're also gonna give it a name, it's called anti. Anti is the happy one. When I do the Newmans, it's gonna be a little easier. But then we have the gauche, and we also have 2 eclipsed. We have 2 eclipsed ones. One where the methyls are eclipsed with hydrogens. It's almost not even worth me trying to use my models, just because if you were in the room, it'd be easier to see. The Newmans might really help the best. So let's show you the Newmans in a second. And then, but I will show the D, the very, very, very unhappy eclipsed. Hopefully you can kind of see this. Everything's lined up and the CH3s are bumping into each other. Everything's lined up. That's, you can imagine that's not a very happy one, right? It's eclipsed and the two CH3s are bumping into each other, right? That's the worst one, the very least happy one, okay? All right, so we have 4. Let's see them. This shows you the Newmans. Anti, everything's apart, right? Happy. Then we have what I'm calling the low energy eclipsed. There's 2 eclipsed. There's a high energy eclipsed and a low energy eclipsed. This one is the low energy eclipsed. Then we have the gauche, where the staggered again. So it goes staggered, eclipsed, staggered, eclipsed, staggered, right? Staggered, eclipsed, staggered, eclipsed, staggered. And it goes, it's going to be the happy one. And then we have a low energy eclipsed. Then you have the gauche. Then this one we're calling, you know, I made up this name myself. It's super eclipsed. Super eclipsed is very, very, very unhappy, right? Because not only are you eclipsed, what's the kind of strain? Somebody say it. It begins with T.
Torsional strain.
Torsional, yeah. Not only do you have torsional strain due to the eclipsing interactions, you also have something called steric strain. And steric strain is a through space thing. So like the 2 CH3s are talking to each other through space. Through space, they're bumping into each other. It's called steric strain, steric strain. You can see it here. See how the 2 CH3s, this is the super eclipsed. See how the 2 CH3s are bumping into each other, basically? They're very close. That's called steric strain, all right? And then you go back to gauche, and then it goes back to the other eclipsed. Now let's see it on an energy diagram. This may help a bit. Okay, so start with anti, happy. Anti is the happy one, right? It's A. We will call it A before, right? Then you go, it goes up in energy to the low energy eclipsed. Low energy eclipsed. Then it goes down in energy. And this one's called, what's this called? The French one. Gauche, right? So anti and gauche. Why is the anti a little happier than the gauche? Can somebody explain it? Why is anti happy?
The CH3s are opposite from each other, whereas the gauche, the CH3s are closer together.
Right, that's right, exactly. Yeah, it makes sense. Things don't like to bump into each other, right? So the gauche, they're happier by being the anti, they're happier being far away, right? Okay, so it goes from anti up to the low energy eclipsed, down to gauche, which is a little less happy than anti. Then it goes up to the super eclipsed. This has, not only is it eclipsed, having torsional strain, it also has a thing called steric strain, and that's the 2 CH3s bumping into each other, right? That is also why that's another reason why gauche is a little less happy. Gauche is a little less happy than anti, because what kind of strain? It begins with S. It's steric.
String?
Yeah. So there's 2 strains. There's torsional and steric. That's it. That's all there is to it, right? Okay, and then once we're at the super eclipsed, it drops down to what again? This is called gauche. Gauche. And then it goes back up to low energy eclipsed, and then back to anti, the happy one. All right. I'm going to try to do this with my models. It might be hard to see. It might be easier on your models. But I'm just going to try to rotate these. The thing I'm going to do, and I'm gonna let's just maybe I'll unshare to try this. Maybe this will be easier. Unshare. You see me, big? All right, you see me big?
Yeah.
All right. So here we are, and what I'm going to do is I'm going to keep the CH3 that's kind of closer to you steady. That CH3 is steady, right? Meaning I'm not going to change it. I'm going to keep that one steady. I'm going to rotate the back one, okay? So this is anti, right? We called anti. What is this? I rotated a little bit. Don't say gauche. It's the something. It's the first one, which we
The
call
low energy eclipse.
low energy eclipsed. Yeah, it's low energy eclipsed. Then we go to this one, which is now the G one.
Gauche.
Gauche, yeah, that's gauche. It's a staggered one, but the CH3s are kind of bumping into each other. They're nearby, so it's a little less happy. Then I go to the high energy eclipsed. You can see everything's bumping into each other, really unhappy. Yeah. What's another way? It's something eclipsed. It's
Super eclipse.
super eclipsed. I made that up. You won't find it in the book. And then I go to the other gauche. Then I go to the other low energy eclipsed. Then I go back to anti. That's all there is to it. All right. Very cool. That is it for chapter 2. I gotta move on to chapter 3 now. If you have questions about this office hours, we can go through it again. But that's the basic idea of this. All right. You just gotta kind of know, there's eclipsed or staggered, and for butane there is a kind of a low energy staggered, a higher energy staggered, a low energy eclipsed, and a high energy eclipsed. And the Newman projections really are good. I would say that I don't know why some students have difficulty with this, but these are, it's a good way to, you see my screen again? Okay. It's a good way to represent this, to kind of show the relative orientation of the CH3s, right? All right. Anti is more favorable than gauche, right? Why? What's the one word answer for that? The gauche has a something interaction. It's steric. Steric basically means the two CH3s are bumping into each other. That's the meaning there, right?
Is steric torsion or steric tension just happening in the across the axis that's perpendicular to the torsional strain?
It's the two CH3s being in proximity to each other. And it's torsional strain, steric strain. Steric strain is the two CH3s being in proximity to each other, okay? Torsional will only occur for eclipsing. Torsional will only occur for eclipsing. So these three guys are all torsional. But which of these has a very bad steric problem too? Left, middle, or right?
The middle?
The middle, yeah. The middle has got a very big steric problem. We actually don't say that the left and right have any steric problem. There's no steric problem with left and right. Why would there be a steric problem with left and right? The CH3s are still far apart from each other. Cool. All right, let's get going on chapter 3. So I'm going to my webcam. My other webcam. All right, so we're into the kind of whiteboard-ish style thing. Like if I'd be teaching this normally, we'd have a whiteboard. Don't have a whiteboard though, but I'm gonna try to play with my webcam here. All right, so this is like the way I'd teach if we had a whiteboard though. So we're in chapter 3 now. And this is reactions of alkanes. Reactions of alkanes. And I said already that we don't have the stuff on the website yet. I'll try to have it by tomorrow. So if you want to get going on the reading and the homework, that'll probably be by tomorrow. Otherwise, you can always look in the book. I mean, it'll be the first couple topics will be identical. All right, so number 1. So in each of these parts, I'm going to kind of like indicate sections, like section 1, 2, 3, blah, blah, blah. So the first thing is strength of alkane bonds. Okay, so as you might imagine, alkanes like a methyl, methane, ethane, propane, there's a bond strength between the bonds, right? And bonds contain energy. Bonds contain energy. Bonds contain energy. That makes sense. Of course, if I have H dot and H dot, if I have H dot and H dot, and they form a bond. So if these two things form a bond, H dot and H dot, you form HH, right? If I have a pair of H dots, they form a bond. And this delta H, which is the bond strength, is negative 104 kilocalories per mole. And we talked about spontaneity of reactions. Is negative a good thing or bad thing, like for a spontaneous reaction?
Good thing.
Good thing, yeah, that's a favorable reaction, right? We can imagine going backwards. For every forward, there's a backward, right? So I could imagine H and H breaking. So the bond could be formed or the bond could break. And delta H should be the opposite. And it is 104 kilocalories per mole. All right. And so, and these H dots, we call free H atoms, free hydrogen atoms. We call them free hydrogen atoms. And we often sometimes call them something else. What do we say if it's a carbon with a dot on it? Sometimes a carbon with a dot would be a radical, a free radical, right?
Oh.
So we've kind of talked about the concept of free radicals. And these are like, it's like a single atom version of a radical. And they're very unhappy, I guess you'd also say. Oh, because they are very reactive. This is not a happy molecule. HH, that's a happy bound molecule. Okay, so this number, we're going to actually give a name. We're going to call it a bond dissociation energy. Bond dissociation energy. A bond dissociation energy. Or what do you think a good abbreviation might be? BDE. So we're going to have a bunch of BDEs. It also has one other name. It's delta DH. Delta DH under standard conditions is called dissociation heat. Dissociation heat. Dissociation heat. So that's all the same idea. It's just the energy that's produced when a bond is cleaved. Okay, that's pretty straightforward. All right, so let's see. All right, so put this down. So maybe a good question is, what are some BDEs of different things? So bonds, examples of BDEs, bond dissociation energies of different bonds. Let's consider some bond dissociation energies of different bonds. This is also in table 3.1 or 3, I think 3.2. So there's a whole bunch of these. We're just going to show a couple representative ones, like HH, which we just mentioned, HH, right? So it's the bond between H and H, which we can kind of, I used my little blue marker to show, like, that's the bond we're cleaving. And what's the BDE? We just said it's 104 kilocalories per mole. 104 kilocalories per mole. What about methane? So H3CH is about a 105. Is that a big difference? it's not a big difference. So the cleaving the bond between CH3 and an H, like basically a methane CH bond, is about the same. 1 to 5, mostly the same. What about H3C CH2H, which of course is ethane. And what about that bond? It's 101. So that's, they're all roughly in the same ballpark, right? All mostly the same. It's a little less energy to cleave that bond, but that's not that big of a deal right now. Let's just keep going with this. What about fluoromethane? F3, H3CF. H3CF is about 110 for that bond. So the little line I'm drawing is representing like the bond we're cleaving, right? So that we're cleaving that bond. I could also just do this, and you could imply that that's the bond we're cleaving, because I made the big long bond. It's like that's the bond we're cleaving, right? Okay, H3CCl is 85. Whoa, that's different, right? That's a huge difference. Would you say that's a stronger bond or a weaker bond?
Weaker bond.
Weaker, yeah. Now let's explore this trend a little bit further and say, well, what about bromine? Bromomethane. You think it's gonna be stronger or weaker?
Weaker.
Be weaker. Let's continue the trend. Yeah, it's 70. So yeah, something weird's going on. Let's keep the trend going. Iodomethane. Stronger or weaker? Probably weaker. 57.
Weaker.
So yes. Yeah, so as we're cleaving these bonds, and I'll just draw a little squiggly, we're showing that we're cleaving those bonds. My squiggly is a little hard to see, but those are just little squiggly lines, right? Okay, so it seems like these are stronger, this is stronger, and this is weaker. So something's going on there. Why? What's the reasoning? Why? Most likely, one way to think about it is the stability of the resulting radical. Stability. So F dot versus like I dot, because those are what's formed. When the bond is broken, that's kind of what's being formed. There's which is the big one? This is big, right? Small. Fluorine is really tiny, and there's a what I call concentrated chart. Actually, the way to see this is on the big one, iodine, with a huge atom, and the radical is kind of distributed over a big surface area. It's a huge atom. Iodine is huge, right? You have this little dot floating around. That's actually kind of stable. More so than when fluorine's tiny. And when you have a single electron on fluorine, it's more of a significant effect. Iodine, it's not that big of a deal. And that's why as you break these bonds and make these larger things, it's happier. It's happier as you go down. It's just about really the size of the resulting radical, fluorine versus iodine, all right? I could say, another way to say that is on the right, it's distributed over more space. Distributed over more space. We're going to see that effect more in this course also, that when you, like big atoms like iodine have special properties due to like a charge or, radical being distributed over more space. Fluorine, all the electrons are concentrated, and it's just, it has kind of weird properties. All right, that's A. Now what about, oops, sorry guys. Okay, so that's A. What about B, which is the other reasoning? there's a between like small atoms and big atoms, there's a varied orbital size and energy. There's a varied orbital size and energy. So an idea, think about fluoromethane versus iodomethane. Okay. What are the orbitals, the valence orbitals of carbon? It's 2s and 2p, right? 2s and 2p. And if you look on the periodic table, fluorine is nearby. It's also 2s, 2p, right? Okay. Now what about iodomethane? Carbon is 2s, 2p, but iodine, you look on the periodic table, where is it? It's underneath a little bit. It's 5s, 5p. So those are the valence electrons. Who has the happy bond? When you have two atoms that are the same type of orbitals, or a bond with totally different orbitals. You can imagine that maybe the fluoromethane is just a happier molecule, right? It's happier, and what does it tell you about the bond strength? The bond strength is happier. So this is a more stable bond, more stable. And this one is a less stable bond. Cool, that makes some sense. That's just an alternate explanation for why, as you go down from like fluoromethane, chloromethane, bromomethane, iodomethane, that the bonds are getting weaker and weaker and weaker. So we have two explanations. One is about the radical stability. The other is really just about the bond, right? Okay, cool. Next. All right, so we did the halogens and those, where were they? The haloalkanes, like chloromethane, chlorobromate, bromoethane. Sorry, we had fluoromethane, chloromethane, bromomethane, iodomethane. Now, let's think about CH and CC bond energies. So we're all still doing the same thing. We're just looking at different bond energies and trying to figure this all out, right? Okay, so what about, let's go back to methane. We already did methane. We said it's 1 of 5, right? These are all kilocalories per mole. Okay. And what did we say about ethane? H3C. ch2-ch. I'm trying to indicate the bond we care about. I'm just showing it by a big long bond, right? The big long bond is the one we care about right now. What do we say about ethane? It was roughly the same, 101, right? What about propane? H3C, CH2, CH2, long bond H. Think it's going to be big, small, same? Roughly.
Smaller?
It's roughly the same. There's not a significant difference. It's also 101. So these are both basically the same. All three of these are roughly the same. Okay. And these okay. One more thing. I'm going to give it a little bit of nomenclature. The radical you make, if I am cleaving this and cleaving the bond and making a CH3 dot, right? I'm going to call that a methyl radical. Methyl radical. I'm just going to write that out on the right. Methyl is a methyl radical. If you cleave the bond, you make a methyl radical, right? CH3 dot. Now this one, what kind of radical are you getting? Now we're going back to our primary, secondary, tertiary nomenclature. What kind of radical? So if this bond goes away and you're left with a CH2 dot, you think that's a methyl, I'm sorry, a primary, secondary, or tertiary radical?
Would it be a secondary?
It's actually primary though, except,
Oh,
sorry,
right.
It's primary because the carbon only has one other carbon on it.
Yeah.
So this is a primary radical. It makes a primary radical, right? Primary radical, primary radical. What about this one? So if that gets chopped, the bond gets broken, you're left with a radical there. Is this a primary, secondary, or tertiary radical?
Secondary.
Still primary, because right, if I cleave this bond, and now we have a CH2 dot, essentially, right? There's only one other carbon on it. So this is still a primary radical. It's just like the other one, primary radical. We'll get secondary, we'll get secondary. We're almost there. Okay, what about H3C CH3H. Now I'm going to explicitly show the bond we care about. So it's like this one. So my little zigzag. Yeah. Okay. And this one is a smaller number. This one is going to be 98.5. So stronger bond or weaker bond?
Weaker.
A little bit
Weaker.
weaker. And the radical, though, if imagine this gets cleaved and you're left with a C dot, is this a primary, secondary, or tertiary radical?
Secondary.
This is a secondary.
Secondary.
Yep, secondary. So this would be a form of secondary radical. All right. So it looks like who's happier, a secondary radical or primary radical, based on what we're kind of seeing here? Because the bond strength is going to kind of be correlated to the happiness of the radical, right?
The secondary.
So secondary radical is kind of going to be the happy one. Yeah. It looks like a primary it looks like a methyl radical is the least happy. Primary radicals are consistently a little happier. Secondary radicals maybe a little happier than that. And who's going to be the happiest of all?
The tertiary.
Tertiary.
What makes them happier? What
Yes,
about
that's a
it?
great question. And that's a major topic. We may have to wait till next time, or we may be able to sneak it in. But there's a very simple explanation. Yeah. Okay, so yes, the tertiary is an example of tertiary. It's H3C, CH3, CH3, and then here's my bond I care about, and I'm going to draw a little squiggly. That's the bond. So normally it's easy to see my squiggly, so maybe I'll make the squiggly smaller just to hopefully I don't confuse people with my squigglies here. Because that's the bond, right? So maybe a mini squiggly. Squiggly, all right, there it is. That bond, when it gets cleaved, makes what kind of radical? Imagine we had a radical on that carbon, it would be a tertiary radical, right? And the number is 96.5. They're all kilocalories per mole. They're all kilocalories per mole. So who's the happiest? Tertiary. That's going to be a theme from now till the end of the course, that primary radicals are the happiest. Sorry. Now, tertiary the happiest, secondary the second happiest, primary the third happiest, and methyl is the fourth happiest. All right. Okay, so we had, what were these? These were all CHs. So we're all just doing CH, different CHs. Let's show some CCs now. So some carbon-carbon bonds also, okay? That's probably where we'll end, is the carbon-carbons. CC bonds. Okay. So we're gonna do some CC bonds. Okay, that's just ethane, right? What if we cleave ethane? So that's a little squiggly again, a little squiggly between the two carbons. This is about 90 kilocalories per mole. Okay, now if I cleave, I'm gonna have the top one. If I cleave this bond up here, so that's a little squiggly also. If I cleave that bond, it's going to be 88. Okay. What about if I cleave this molecule, and I cleave this one? So you can envision, like in the top, what kind of radicals am I getting? There'd be a something radical and a something radical. If you get 2 methyl radicals, those are not primary. So don't, primary is different than a methyl. The methyl radical is a very unhappy radical, right? Here, you'd form a methyl radical and a secondary radical. How about here, there'd be a methyl radical and a what kind of radical? That's the carbon has 3 things on it, so tertiary, right? This would form a tertiary radical on top, and this is 87. So we're seeing a trend here, right? These bonds are getting you're going from strong to weak as we go down. Let's do another one. Now this is the crazy one. We have CH3, CH3, CH3. Then we have here CH3, CH3, CH3. Okay. All right. We cool with that? This is the bond we're going to cleave. Little squiggly right there. I got to figure out this camera flashing problem. I'll do that next time. Okay, so if we cleave this bond, what kind of radicals are we getting? Top one will be a what kind of radical?
Tertiary?
Tertiary. The bottom will also be a
tertiary.
And we said that tertiary are the most stable, right? The happiest.
Yes.
Yep. So is this going to be a big number or a small number?
Small number.
Very small. Relatively speaking, it's super small, 78.5. So it's actually very, very small in this series. And as we went from going from the top to the bottom, it's like strong CC bonds, weak CC bonds, right? Went from strong up top all the way down to weak on the bottom. And what I'm going to close with is just what I already told you. I'm just going to say it one more time. So why do we have these trends? The answer is the stability of the alkyl radicals varies. Stability of alkyl radicals varies, right? And we can just say it this way. We can say that in terms of the stability, the tertiary radical, which is like that, is more stable than a secondary radical, which is more stable than like a primary radical, which is more stable than what kind of radical? Begins with M.
A methyl radical?
Methyl radical. So that's where we're gonna go next, is explaining why. Somebody already asked why this is the case. I have it if you want to stick around for office hours. I always do these little mini office hours after lecture. So if you want to hear like the 2-second story about it, I can tell then. But otherwise, I'm going to stop the recording and stop the lecture, and we're doing good. This is some fun stuff. We're getting into a really cool reaction having to do with radicals and halogenation, like attaching of chlorine to alkanes via radicals. So that's where we're heading with this really cool chapter 3 stuff. And we just need to know about like radical stability first, right? So that's what we're talking about, is what are the stable radicals and what are the unstable radicals. All right? Cool. All right, I'm gonna stop the recording. And if you want to stick around, We'll chat a little bit more.
So I have a question.
Let me stop the recording real quick.
Okay.
Oh, sorry, the Zoom is being weird. I just need a second. Oh, there it is.